today I'm going to be showing you how I can scan this. You might be wondering what this is. Well, it holds up pieces of paper and posters, like this. A friend of mine gave me this. He has a magic show, and he uses this to hold up his pictures. This can be used for smaller things, but it can't be used for a lot bigger. A great thing about scanning these is that you can scale it to the size you want. Okay, so I've applied some stickers using these special tweezers. So the scanner has more reference points. The scanner is a GoMscan 1. So what we're going to do is we're going to turn it on and scan it, but it's not going to get into the little crack. It takes a lot of little pictures to get a model formed. And we want it to scan the whole thing, so we're going to move it down. As you can see, we've missed some mesh around it, so we're going to reposition the scanner and then start again. We're using this turntable so that we can see every side of it.
All right, now that we have captured the data, we need to first align the data so we have some orthogonal coordinates to work with. That means we have a coordinate system where up is up relative to the plate, and then we have some really nice left and rights. And so we did that in Zeiss Inspect, and so now we have two mounds as shown here. However, as Lana explained, the GoMscan 1 doesn't have the triple scan feature of the ATOS Q, and so we're left with data that is missing in between these two mounds. However, we can show how to overcome this through the reverse engineering process. So to do this is we go over to Geomagics Design X and we import the mesh. Make sure that we have it in millimeters. We're going to import, and the part comes in those orthogonal coordinates that we made, and we can see that we're missing some data. So we're first going to construct a plane, and we're going to do this on a point that's just a little bit above where we kind of started losing data. And we're going to make sure that we have that plane that is going to be aligned to our base plate like this. So it doesn't look like I got quite the right spot there, so I'm going to bump that up here, tell it to be orthogonal again, and there we go, it looks great. Now we're going to use the mesh sketch feature, which is really awesome. And so we're going to be able to take a section of that. And so right here, it is showing a little bit of a cropping. So we're going to go ahead and take that. And to keep things simple for right now, let's just work with one mound. So we're going to go ahead and just capture the mound on the right, like that. And now we have an auto sketch feature, so we're going to come in here, we're going to deselect that curve, and we'll take all these curves. And so we already have a really good outline. And I didn't have to do much work at all. However, I do have a little feature down here that is not exactly what I want, so I'll just fix it like this. And I'll tell this I want it to go over there, and I'll give it a constraint to be coincident. And I select that backwards, so I actually want to go here to here and go coincident. Okay, that looks good. And that'll be good enough for us right now. So we're going to come up over here. Now we have a nice section. We're going to just approximate the top of this feature. This is an injected part, so the tolerances are not going to be critical. We can tell that there's a little bit of a draft angle. And so if we put about 6 degrees, just by looking at it from the side, that looks like it's going to be quite accurate. And so then we will then have one in the opposite direction as well, like that. And so just looking at the part from the side, like this, we can tell that that is a pretty good approximation to the part. So we'll go ahead and keep it. Now we have a solid of that mound here. And now we want to go and clean up the top. And a simple way of doing that is to use a fillet. So we're going to take a fillet all the way around like this. There we go. And there's a really nice feature here. We can kind of play around with the size of the radius here if we want. But there's a really great feature here that will allow it to just go find the right size. And so that came out to a really perfect size right there. I didn't have to spend a lot of time with that. And it just went and found an optimization between the mesh and this CAD feature. So that's wonderful. So now what we have, if we look at our deviation map, is we have filled in that data that was not there, and we see that we are very close. We're 0.008 of an inch for an injection plastic molded part that's going to be 3D printed. This is just fine. You know, here we're 5,000 in. That is acceptable for this application. So now we just do the other side and then work on the base plate. So here's the part when it's complete. And here's what the deviation map looks like for the whole part. You can see we've captured both mounds. And if we go over here and hide the mesh, we are just left with the heat map of showing the deviation. You know, for an injected part like this, we are only, 5/10,000ths of an inch right here. That's really good. Looking down here, 20. That's kind of like the size of a hair. And then inside this, inside between these two mounds where we had no data, we now have data. And just looking at some of the points, worst case is about 0.060. That's going to be just fine for this part. So if we take the heat map off, we can see that we are now done. We have a solid part that was created from the GomeScan 1, and we're able to get the data in between here without having to step up to another system by using the Geomagics Design X software. As Lana said earlier, we could have obtained this data with the Atos Q because it has a triple scan. We could have even maybe used the touch probe capability of the Atos Q, but for this example, we wanted to keep it how it was.
Today we've learned how to reverse engineer and scan this part with a GomeScan 1.